Leaf wetness sensors are typically used to forecast and prevent foliar diseases like rust and blight. They're also used for crop spraying, frost monitoring, and quantifying water storage in the plant canopy. Some engineers have started using the sensors for measuring surface wetness on buildings and walkways, and a few have even been used to study the effects of moisture-related degradation of statues. The leaf wetness sensor detects when leaves in the canopy become wet and how long they stay wet. The concept is pretty basic. When the canopy is wet, the sensor reads wetness. When the canopy is dry, it doesn't. In order to do that, the leaf wetness sensor measures the dielectric constant of a zone approximately 1 centimeter from the upper surface of the sensor. Since the dielectric constant of water and ice are much higher than the dielectric constant of air, the measured dielectric constant can be used to detect the presence of moisture or frost on the sensor surfaces. Researchers have been using resistance grids to detect water on leaves for a long time, but historically it's been a frustrating endeavor. The original sensors were just gold traces on a circuit board. When a drop of water bridged the gap between the traces, it counted as wet. The problem was that you had to have a large droplet to bridge the contacts. Because dew is composed of small droplets, the sensor would often not sense anything even when the canopy leaves were wet. So researchers started to paint the circuit boards with latex paint. But latex is hygroscopic, and as the paint takes up water, its resistance changes and gives a positive signal. But latex paint takes up water at relative humidities of about 70%, and researchers would get false positives. So then people tried painting their sensors, baking them to drive off the hygroscopic elements, sealing them in 100% humidity, setting a wet-dry threshold, going as far as calibrating each individual sensor themselves. The whole process became a big pain. At Decagon, we wanted to make a sensor that you wouldn't have to paint, bake, or calibrate. One that would be accurate right out of the box, and we're pretty certain that measuring dielectric constant was a better method than the old resistance grid sensors.
It turned out to be a serious challenge. We had to find the right surface coating that was hydrophobic, UV resistant, and had the same shortwave reflectivity as a real leaf. We struggled a little bit with temperature sensitivity in the beginning, but the real problem was actually verifying that the sensor dried off at the same rate as a real leaf. It took a couple of years in research and development, but ultimately the sensor we developed mimics a real leaf pretty well. It mimics the radiative properties of a real leaf and has a similar thermal mass to real leaves, but most importantly, it dries off at the same rate as real leaves. It also is extremely sensitive to even tiny amounts of dew or even frost.
The leaf wetness sensor offers a great alternative not just to older leaf wetness sensors, but to leaf wetness modeling. Calculating leaf wetness from environmental variables is complex and inaccurate. It takes all kinds of variables to do it right: air temperature, relative humidity, radiation, wind speed in the canopy. There's a lot of room for inaccuracy. The leaf wetness sensor is a simple solution. Instead of calculating leaf wetness, you can actually measure it. Every sensor is factory calibrated, and there's very little sensor-to-sensor variability. The sensor tells you when the leaf gets wet and how long it stays wet. It's a great solution right out of the box. Best of all, the leaf wetness sensor plugs and logs with all Decagon loggers and is also compatible with Campbell Scientific data loggers. If you have questions about buying or using a leaf wetness sensor, visit decagon.com/LWS.